Okay. Bismillah ar-Rahman ar-Rahim. We'll continue. We reach this theorem where it says if the sequence is bounded and monotonic, then it converges. Yeah, be careful. Actually, what we need, look, if the sequence is increasing, going up, and it's bounded above by something. So we have increasing and bounded above. Then for sure it will converge. And the same thing, decreasing, but bounded below by something. It decreased, but it will not go to minus infinity. It will, this one, it will not go to plus infinity, so it will go to a value. So I have decreasing and bounded below. Let's talk about it in general. If a sequence is bounded and monotonic, either increasing or decreasing, for sure, then this one will be correct. Then it will converge. Yeah. So let me deal with the first one. I need to check it's bounded and monotonic. I think this is a very easy one. Part A. This sequence. Yeah, I have an plus 1, which is 1 over n plus 1. This will be less than or equal 1 over n. Actually, less than 1 over n. Yeah. And it will equality, which is an. So the sequence is monotonic. An monotonic. Actually, it's decreasing. And also the sequence an is between 0 and 1. So it's also bounded. So according to the theorem, this sequence converges. By the theorem will not tell you it converges to what, but it will converge. It's easy to check this one converges to 0 since the limit is equal to 0, but just to apply the theorem. This another one, n square over n plus 1. Yeah. How to check this one? Yeah, I need to check monotonic. By the way, it's not bounded. I cannot make a bound for it. It's bounded below only. Yeah, it's bounded below because it's n square over n plus 1, always greater than or equal to 0, since I have n is a positive value. It's greater than or equal, yeah, greater than 0. Let's see. So it's bounded below by 0, but you cannot prove it's bounded above by something, because this one will increase more than this one as n goes to infinity. Actually, the limit goes to infinity, very clear. Okay, now how to show it's monotonic? I can use this. Either I can use bn plus 1 less than or greater than bn, or the other way. Let me check f of x. Let me check it through the derivative. So I have bn at b. This is part b. Bn is n square over n plus 1. I'm not sure what it will work or not, but let me see what will happen. I have f of x square over x plus 1. So I need to find the derivative. That will be 2x times x plus 1 minus x square over x plus 1 all square. And that is what? 2x square minus x square. That will be 2x plus x square over x plus 1 all square. Am I right? Yeah, 2x square minus x square plus 2x, which is I can write as x times 2x x as 2 plus x over this. So let's check the signs. Let me check it here. If I check the sign, that will be, I need -1, I need the 0, and I need the -2. So before the -2, take -3, that will be negative, negative, that will be positive. -2 and -1, take -3 over 2, this is almost positive, that will be positive, negative, that will be negative. -half, for example, this is positive, this is positive, this is negative, still negative. More than 0, take 1, positive, positive, so it will be positive. So f of x greater than equal to 0 for x greater than 0. F prime of x, I mean. So f is increasing for x greater than 0. So that means the sequence Bn increasing for n greater than 0, which is always, this is n actually, it's from 1 and so on. Okay, so it's increasing, so it's monotonic. Yeah, so this is clear, monotonic. Cn is an easy one, because Cn is what? If n equal 1 is -1, the sequence Cn, -1, 1, -1, 1. So I can say Cn is between -1 and 1. Yeah, it's bounded then, but not monotonic. Not monotonic. Because it will oscillate. So we cannot discuss that. Actually, I know it's diverges, and this one also diverges. Okay. But be careful. We say the sequence, if its sequence is bounded and monotonic, then it converges. If one of these conditions were not satisfied, we do not say it will diverge. It doesn't mean that the sequence will diverge. The sequence, this theorem is only one direction. It's only one direction. Okay, let me do these problems from the book. I said, since this is the new concept, so I would try to do it with all the cases. By the way, some of them I think we need to use the calculator. We cannot do it easily. Some of them you can discuss it, but some of them it will be difficult to do. I'll try to do as much as I can. Okay, 53. Actually, these are the 8 problems in the book. These about the theorem. I choose some of them. Okay. N is 4 minus 1 over n. Yeah, very clear. N plus 1 will be 4 minus 1 over n plus 1. And that is, yeah, notice in 1 over n greater than 1 over n plus 1. That implies minus 1 over n less than minus 1 over n plus 1. So that means this is less than 4 minus 1 over n. Or the other way. No, it will be the other way. Yeah. An, this one is less than, minus 1 over n will be less than this, since I multiply by minus. No, be careful. Minus 1 over n. 1 over n is greater than this. Times minus, yeah, it will be less than. Yes, you're right. So that will be less than 4 minus 1 over n plus 1, which is an plus 1. So the sequence is decreasing. So an is less than an plus 1. So an plus 1, the sequence is increasing. Okay, sequence increasing, monotonic. Also the sequence, yeah. I can say the sequence, this 1 over n cannot exceed 1. Cannot exceed 1. This is always less than 1. So an, which is 4 minus 1 over n, will be less than 3. No, be careful. Yeah, 1 over n is less than 1. So that means minus 1 over n is greater than minus 1. So this will be greater than 4 minus 1, which is 3. This for sure, it will be more than 3. And also, let me try to do it in a nice way. I know 1 over n is less than 1. So I have minus 1 over n greater than minus 1. Then 4 minus 1 over n greater than 3. And also I know that 1 over n is greater than 0. That means minus 1 over n is also less than 0. So that means 4 minus 1 over n will be less than 4. So this sequence, which is 4 minus 1 over n, is between 3 and 4. So it's bounded. So for sure, this sequence converges. I know it's converged to 4. Yeah, but this is the way to think about it. Okay. Let me do the next one. 54. An is this. 3n over n plus 2. Yeah, I'll do it with the function 3x over x plus 2. What will be f prime? F prime will be 3 times x plus 2 minus 3x over x plus 2 square, which is 6 over x plus 2 square, which is always positive. So f is increasing. So the sequence monotonic. F is increasing. Also, check. You know that 3n. Actually, do it the same way we did this. N over n plus 1. What is it? Yeah, like this one. We'll do it the same way. 2n over 1 plus n. Check it's bounded. Okay, did it here, yeah. So for n greater than 1, yeah. Let me do it. So I have 3n is actually n plus n plus n. And that will be greater than n plus 1 plus 1, since it's greater than 1, which is n plus 2. Okay. Yeah. So that means 3n, if I divide by n plus 2, would be greater than 1. It will be greater than 1. So it will be bounded by 1. Or it can be bounded by 0, actually. It's greater than 0 or greater than 1. It's the same idea. And also, if we deal with 3n, or not 3n, I know n over n plus 1 is less than 1. Why? Or we can do it this way. I know n is greater than less than n plus 1. Very clear. So I have n over n plus 1 less than 1. So 3 times n over n plus 1 is for sure less than n. So this sequence, actually it's bounded between 1 and 3. So it's bounded. Only the above and below. Yeah. $55 is not an easy one. I'll do 55 in the next line. I'll do 50. Let me do 56. Easy. I think let me do 57. Okay, where an is 2 over 3 to the power n. Yeah. I know 2 over 3 to the power n, which is an, that will be greater than 2 over 3 to the power n plus 1, because this is less than 1. So we take the next power, for sure it will be greater than this. So it's monotonic. And also, I can say an will be greater than 0 and cannot exceed 2 over 3. Why is that? Because they know this, always the next one would be less than the first one. I know in the 2 over 3, because of this, this one is less than 1. So we have something to the power less than 1 value. If have, let me do it here, because this is important. If r is less than 1, or less than 1, then I have r will be greater than r square, and that will be greater than r cube, and so on. Oops. So that means r to the power n will be greater than r to the power, let me see, r is positive and less than 1. Then r between 0 and 1, then r is greater than n plus 1. Yeah, if we have half, then it will be 1 over 4, 1 over 8, and so on. Always it will decrease. So that means what? That means r will be my highest value, will be the bigger value. So r to the power n always less than r, less than or equal to r, because r square will be less than r, less than. I'm talking about r between 0 and 1. And it's always greater than 0, because it's positive. So this one bounded the sequence, this sequence between 0 and r, which is this one. I hope it's clear. This is if the value is positive and less than, between 0 and 1. This is between 0 and 1. I think it's very clear from here. Yeah, I have Rn is greater than Rn plus 1. This is for any R. Not only that, R is the biggest value for it. Okay. Now let me go back to 55. Yeah, 55 is not easy to do. You need to check the values. I don't think you can do it easily. Yeah. So I have, what will happen? I have A1. What is the AN? Let's go right. AN is, which is a strange one. N times the power n minus n over 2. If we do the calculation, A1 by the calculator, I mean 65th. A2, it will be 0.7358. A3, it will go back, and so on. You need to notice one thing. Yeah. Now, if I want to check increasing, decreasing, f of x will be x e to the power minus x over 2. So what will be f prime? F prime will be e to the power minus x over 2 minus half x a minus x over 2, which is a minus x over 2 times 1 minus x over 2. This is always positive. And you should notice this one. Let me check it here. 1 minus x over 2, which is 2 minus x over 2. This is negative if x is greater than 2. So this is negative for x greater than 2. Yeah. So that means this sequence, if you take the values, it will be not monotonic. This one, yeah. This, I notice A1 is less than A2, but A2 is greater than A3. But what I get, this sequence, for n greater than 2, it will decrease. So A2 will be greater than A3, and A3 greater than or equal 4, and so on. It will decrease after the second term, because this is what we get from here. So it's monotonic, actually decreasing for n greater than 2. If that is the case, it means an, because after A2 it will decrease, so an will be less than A2, and for sure it's positive. So an with positive and less than 0.7358, which is A2, which is unit reason to do this. So it's bounded now, so it will converge for n greater than 2. Like you need to check it for n goes to infinity, so this is okay. Okay. Now let me do 56. Actually, I need more space. It seems to be. What is 56? It's minus 2 over 3 to the power n. Minus 2 over 3 to the power n. This is my n. Is this one bounded? Yes. Yeah. But it's not monotonic. Not monotonic. Why? Because I have, if you take the values, it will be minus 2 over 3. Then at n equal to, it will be 4 over 9. Actually, negative, positive, so it will not, it's minus 8 over 27, and so on. Very clear, not monotonic. Let's go negative, positive. So it's not monotonic. I cannot say it's increasing, decreasing. Yeah. However, the absolute value of these values, if you take the absolute value of this one, which is absolute value of 2 over 3 to the power n, I know this one will be less than 2 over 3. So this sequence be between minus 2 over 3 and 2 over 3. So it's bounded. Let me do 57. 57 we did, huh? Yeah. We did 57. Now we'll do 58. An 3 over 2 to the power n. Since this is greater than 1, so what will happen? Let me do this. If r greater than 1, then r to the power n will be less than r to the power n plus 1. Yeah. So this is greater than 1. So for sure, if you square it, you're getting bigger values. If you make it cube, then we get bigger and bigger and so on. So this sequence, so we have an 3 over 2 to the power n. For sure, it will be less than 3 over 2 to the power n plus 1, which is an plus 1. So the sequence monotonic. The sequence is monotonic. n less than, so n plus 1 greater than, that's increasing, actually, but not bounded. For sure, it's not bounded because the limit of an as n goes to infinity, it will be infinity. Value more than 1 to the power infinity, that will be infinity. Let me do the next one, 59. An equals what? Sine n pi over 6. If we check it, that will be sine pi over 6, then sine pi over at n equal 2. It will be pi over 3, then sine pi over 2, sine 4 pi over 6, and so on. So it depends on the values of sine, and we know that the values of sine are oscillating. Yeah, going to a value, then this is will be, yeah, this is will be what? Will be half. Then this is square root 3 over 2. This is 1. Then it will go down again. That will be what? 2 pi over 3, which is square root 3 over 2. So it will go up and down. So it's not monotonic. And actually, it will go to negative value then. So for sure, it's not monotonic. But I know that sine by n pi over 6, I can bound it between -1 and 1. So it's bounded, but not monotonic. Yeah. Let me do 60, which is cosine n over n. Which will happen the same thing. It's not monotonic. Easy to check, it's not monotonic. Yeah, because this is will make it going up and down. It's not monotonic. Actually, sometimes going the negative values, so it's not monotonic. Yeah. Oops. Is it bounded? Yeah, I can say an is always less than or equal to 1, so it's bounded. Because cosine n is always less than or equal to 1, so between -1 and 1. But about it, that will not make a big difference. Okay. Let me do this. I choose 2 problems from here. And to show they are converges by using this. They are bounded and increasing or decreasing and monotonic. I need to prove both. Okay, 61. I have this sequence, n is 7 plus 1 over n. Very clear, I know in 1 over n is greater than 1 over n plus 1. So that means 7 plus 1 over n. That means an, which is 7 plus 1 over n, will be greater than 7 plus 1 over n plus 1, which is an plus 1. So the sequence decreasing, so monotonic, because it's decreasing. Not only that, I can prove easily. I know in 1 over n, this is an is greater than 0, very clear. And I know in 1 over n is less than 1, so that implies 7 plus 1 over n will be less than 7 plus 1, which is 8. So an is greater than 0 and less than 8. Yeah, so it's bounded. If it is monotonic and bounded, for sure this sequence converges by the theorem, this theorem 9.5, which we discussed before. Yeah. This is bounded and monotonic, then for sure it converges. There's this theorem. This is what he wants us to do. Okay, 63, which is almost similar. Let me just simplify it first. AN is what? Is 1 over 3, 1 minus 1 over 3 to the power n. Okay. I know when 1 over 3 to the power n, let me do it the other way. 3 to the power n plus 1, this is greater than 3 to the power n. That implies 1 over 3 to the power n plus 1 will be less than 1 over 3 to the power n with a minus sign. So I have minus 1 over 3 to the power n plus 1 greater than minus 1 3 to the power n. So I have an plus 1, which is 1 over 3, 1 minus 1 over 3 to the power n plus 1. This is less than, greater than 1 over 3, 1 minus 1 over 3 to the power n, which is an. So for sure it will be increasing monotonic. Now to make it bounded, yeah, I notice 1 over 3n is between greater than 0 and less than 1. That implies minus 1 over 3n. It will be greater than minus 1 and less than 0. Then you do the rest. That will be add 1. You have 0 is less than 1 minus 1 over 3 to the power n less than 1. Multiply by 1 over 3, which is a positive value, so it will be 0 less than 1 over 3. So it's bounded also. So for sure the sequence an converges. Actually, it's easy to do. This goes to 0. It will be 1 over 3. Yeah. Yeah, there are some problems where we explain, where we define the sequence by a recursive way, recursive definition. How to deal with such problem? Yeah, the problem is that we need something called mathematical induction. Mathematical induction. What's the idea of the mathematical induction? If I want to prove something like an expression or something is true for all n greater than or equal to 1. So I follow these steps. The first step, I verify it's true at a value. Usually we do it at 1. This is my first step. Second step, I assume if it is true at k step, at step number k, then I prove the next step is also true, provided you know so the step at n equal k is true, lies, and the next step is true. If I can do these two steps, then that means this expression is true for all n. Okay, and this is what I will do. And this is what we will do. Okay. So first, if I do numbers, let me do this one. A1 equal to an plus 1 equal this. So half times n plus 6. If we do the numbers, I have 2, then I have 4, then I have 5, 5.5, 5 points, something like this. It seems it's increasing. Yeah, it seems an increasing. And cannot exceed and an less than 6. Cannot exceed 6. And this is what I will try to prove by induction. So my first one, I want to prove that an plus 1 greater than an. I want to prove this for n greater than or equal to 1. So I will follow these mathematical inductions. So my first step, basic step, they call it, let me call it A, capital A. I need to check on the P at 1. What is my P here? P of n is half, is an, is my an. Okay, or an plus 1. Okay, it's okay. So B at 1, it is 2. A1, which is 2. And B at 2 is what? We check it, it's 4. So it's greater than B of 1. So at an step, which is at n equal 1, this is true. So this is basic step is true. I have this is A2, which is B at 2. So it's greater than A1. Okay. Now we'll do the second step. I assume Pn is true. Pn is true for n equal k. That implies I have ak plus 1 is greater than ak. And I want to prove that Pn is true for n equal k plus 1. So I will start with ak plus 2. Oops. I left the space. Oh, good. So it means we want to prove ak plus 2 greater than ak plus 1, provided ak plus 1 greater than ak. Okay, so let me start with ak plus 2. ak plus 2 will be what? It will be half ak plus 1 plus 6. Okay. And since ak plus 1 greater than ak, so this is will be greater than half ak plus 6. And what is half ak plus 6? It will be ak plus 1. That will be ak plus 1. So I proved this. So that means the sequence, so that means in no P of n is true for all n. So that means the sequence, I have proved that the next step is greater than the first step. So the sequence increasing, which is, we can say it's monotonic. Okay, now we did the first one, monotonic. Now I need to prove it's bounded. Okay. Yeah, let me just remind you about the sequence. A1 equal this, an plus 1 equal half. Yeah, half an plus 6. We want to prove an is bounded. Very clear, an is greater than 0. It is very clear. Now use mathematical induction. to show that an is less than 6. It's bounded above by 6, cannot exceed 6. So I will do the same thing, the same steps. Step 1. Step 1. Yeah, we call it A and B. Yeah. Step 1. Yeah. P at 1, which is A1 equal to less than 6. So it's very clear this was correct. Step 2. I assume إنه AK is less than 6 and we want to prove AK plus 1 less than 6. So what is AK plus 1? AK plus 1 will be half AN plus 6, AK plus 6. And I know this less than 6. So this will be less than half 6 plus 6. And that is what? 6. So I'm getting AK plus 1 is less than 6. Then that means what? Pn, An less than 6 for all n greater than or equal to 1. So An is bounded sequence. Is bounded sequence. Okay. Now we prove it's monotonic and bounded. That means the sequence converges. Can I find what it's called converge to what value? Yes. How? Since it converges, it will converge to a value, call it L. So that means the limit as An as n goes to infinity is equal to L. Not only that, and also the limit of An plus 1, but it will not make a difference as n goes to infinity is equal to L. So I apply this, I have this expression. So take the limit as n goes to infinity. What you will have? Here I have L, half L plus 6, and solve this equation. What you will have? 2L. You have 2L equal L plus 6. So L equals 6. So this sequence converges. Not only that, it will converge to 6. That limit will be 6. Okay. Yeah, in one of the old exams, we have this problem. Okay, which will do the same idea. Yeah, if you notice, A1 will be square root of 2. First, I need to write it similar to this way, recursive way. Then A2 will be square root 2 plus the square root of 2, will square root 2 plus A1. A3, square root 2 plus the square root 2 plus the square root of 2, which is this. So it's 2 plus A3. So the recursive definition will be what? A1 is square root of 2, and they have An plus 1 will be square root of 2, and this is A2, sorry, plus An. And this is what I will work out. Work out this sequence for n, 1, 2, and so on. Okay, I'll do the same thing. Yeah. A proof it will converge. It's monotonic and bounded. Compute the first 5 terms in the sequence, which I need calculator to do this. I will not do it. I'll write a recursive formula. We did this. Yeah. Find the limit of An. Yeah, to find the limit of An, it's a recursive formula. But I need to prove first that the limit exists. Actually, we'll do it in the exam just to save time. We said it's a convergent sequence. Yeah, it's a convergent sequence. So no need to prove it's bounded and monotonic. But let us prove it's bounded and monotonic in this case. Yeah. How to prove it's monotonic? This sequence n is monotonic. How to prove that? Yeah. Yeah, you know what? I will prove first it's yeah, let me prove first it's bounded. I think it's easy to do. It's bounded. Yeah, and it seems to me that it's bounded by 2. So we say want to prove an is between 0 and 2. This is easy to do. So I need to check this. So we'll do the same way. A1 with square root of 2 is less than 2. So the first step is correct. Assume it is true for n equal k. So that means ak is less than 2. And proof ak plus 1 less than 2. Check ak plus 1. Ak plus 1 will be what? Will be square root 2 plus ak. And this is less than 2. So this is less than 2 plus 2, which is 2. So ak plus 1 greater than 2. So that means the sequence an less than 2 for all n greater than or equal to. So it's bounded. We prove it's bounded. This is the first thing. Now I want to prove it's monotonic. How to prove it's monotonic? It's not an easy task to do that. Actually, it's tricky to prove this. Yeah, I need to start with this. This is correct. An minus 2 times an plus 1. This is less than or equal to 0. It's always correct. Or n greater than 1. Yeah, this is positive. This is negative. Since an is less than 2. So that means an square minus an minus 2 is less than or equal to 0. And that means an square is less than or equal an plus 2. Now this is positive, this is positive, so I can take a square root, and no need for the absolute value because it will be positive. This an will be less than or equal an plus 2. And what is this? This one is the next step. It is an plus 1. So I have an less than an plus 1. Yeah. So it's decreasing, not decreasing, increasing monotonic. Using this trick. So this is negative because n less than 1. Because of that, I started with being bounded. So that means the sequence converges because it's monotonic and bound. How to find the limit of this? we'll do the same trick. I have AK plus 1, AN plus 1, square root 2 plus AN. And they know, because it converges, that means the limit of AN as n goes to infinity is equal to a value L. And the same thing, the limit of AN plus 1, it will not make a difference. That will be L. So take the limit as n goes to infinity. We have what? L square root 2 plus L. Solve for L, square it. R square equal to plus L. So you have L square minus L minus 2 equals 0, which is I can factor it as L minus 2, L plus 1 equals 0. So I have L equal minus 1 or L equal 2. L equal minus 1 is wrong. Why? Because if we apply it here, we have 1 is equal to minus 1, which is wrong. So I have the limit as n goes to infinity of AN is equal to 2. Yeah. I'm getting to that. Okay. Now, by the way, this is the idea of bounded and monotonic. Usually it does not come in the exams. Mainly the exams, it's about finding the limit for the sequence. If you look at these problems, sometimes it comes with these bounded and monotonic, but usually it comes with the finding the limits. So let me do some all the exam problems, and then I will stop the recording. Okay, we have this sequence. Okay, so I have the sequence is e to the power n plus n over e to the power n minus n. I want to check the limit as an as n goes to infinity. This mainly the things. I need to find this limit. Which is this limit? an plus n over an minus n. I'll do this trick. I will make it f of x or f of n, let me say, equal an. And then I will work out the limit of f of x as x goes to infinity. Yeah, we did it before. We did this idea. So I have what? E to the power x plus x over e to the power x minus x. So that means use Lewitter's rule. You have what? Limit. No need to use Lewitter's rule. Let me take limit x goes to infinity because I have something here, problem here. So I have e to the power x common factor. You have what? 1 plus x is minus x over e to the power x 1 minus x is minus x. Yeah, so this is cancelled. Now we need to do this limit. Limit x goes to infinity of x e to the power minus x. See what will happen. If you apply it, you have 0 times infinity. So do this trick. Limit x goes to infinity x over e to the power x. Now this is infinity over infinity. So I can use Lewitter's rule. So I have limit x goes to infinity 1 over e to the power x, and that will be 1 over infinity, which is 0. So I have this limit is what? 1 plus 0 over 1 minus 0, which is 1. So it's convergent, and its limit is 1. This one, I need to find this limit. Let me go to the function right away. F of x is tan inverse of square root 60x plus 7 over 20x plus 9. So we'll find the limit as it goes to infinity of tan inverse square root 60x plus 7 over 20x plus 9. That I can take the limit inside and take the limit inside the square root also. So that will be tan inverse square root. Now I'll put the limit here. 60x plus 7 over 20x plus 9. And this is the same degree. So that will give me tan inverse of the limit square root. What will be the limit here? I have same degree, so it will be 60 over 20. So that will be tan inverse square root 1 over 3. What will be that? That will be tan inverse 1 over square root of 3, which is, when that through, oh, sorry, 6 over is 3. Yeah, that will be square root of 3. I know tiny by square root of 3 is 5 over 3. Sorry about that. So this is the correct answer. 6 over 30 is 20 is 3, not 1 over 3. Okay. This sequence converges, diverges. Yeah. How to do it? We need to check the limit as n goes to infinity of this sequence. Yeah, I think we can do it by the squeezing theorem. I know sine square n is between 0 and 1. Divide by over 2 to the power n, then this is 0, and 1 over 2 to the power n. I know this goes to 0 as n goes to infinity. Limit. This is well known. This is very equal to 0. So this limit goes to 0, and this limit goes to 0. So this is by the squeeze theorem goes to 0. So it converges to 0. The number of the n term of a sequence is given by this. He want the limit, I mean, the limit of the n term. So he want the limit of an as n goes to infinity of this an. So I can have two things. I have the limit as n goes to infinity of 1 over n sine n pi over 4 plus 3n cubed plus 6n squared plus 1 over n cubed plus n squared plus 4. So you have these two expressions. I will do it one by one. Yeah. So what will be the limit as n goes to infinity of 1 over n sine n pi over 4? That will be what? Equal to what? Let me do this first. Yeah, I know no sine n pi over 4 is between -1 and 1. So sine n pi over 4 over n, which is positive, greater than between -1 and 1. This goes to 0 as n goes to infinity. And this goes to 0. So this is by squeezing theorem goes to 0. For the other one, limit as n goes to infinity of 3n cubed plus 6n squared plus 1 over n cubed plus n squared plus 4, same degree. So it will be 3 over 1, which is 3. So that is 0 plus 3, which is 3. So it's converges to 0, to 3. This sequence, I think, is an easy one. We did it something similar, actually. So I have the limit as n goes to infinity of tan 2n pi over 1 plus 18. As I said, mainly it's a limit problem. That will be tan, since tan is continuous in its domain, over 2n pi over 1 plus 8n. That will be tan what? The same degree, 2n over 2n pi. Let me be careful. Over 8n. That give me what? Tan pi over 4. Yeah, this n cancelled, so you have pi over 4. That's equal to 1. So it's converges to 1. And sine pi over n. Let me try to do this limit. Limit n goes to infinity. N sine pi over n. Now, by the way, if we do the squeeze theorem, then we'll be in trouble, because you multiply by n, so you have minus n minus this. So that will not, I'm not getting the same value here. So be careful. So I need to do it in another way. Yeah, I can do it this way. I let t equal 1 over n. So I'm getting what? T equal pi over n. Let me make it. Yeah, so that I can make it t. So I have limit. If n goes to infinity, then t goes to 0. Here I'm getting n is pi over t. So I have pi over t sine t. And that will be limit t goes to 0 pi sine t over t. I know this is 1. This limit is 1, so I have pi times 1, which is pi. So converges to pi. This one, I take the limit inside. I think is an easy one. 1 minus sine n pi over 2n plus 1. This limit is 1. This one, I can take the limit inside. That will be sine limit n goes to infinity. It's a limit problem. As you notice, always it's a limit problem. So it will be 1 minus sine. That will be what? N pi over 2n. So it will be 1 minus sine pi over 2. And that will be 1 minus 1, which is 0. Converge it to 0. The sequence is converging to what? This sequence, if we rewrite it, that will be 1 plus n sine 1 over n. So mainly we need to do this. So I need to find the limit as n goes to infinity of an. That will be the limit as n goes to infinity of 1 plus n sine 1 over n. Yeah, that will be what? 1. Yeah, let me do this limit aside. N sine 1 over n. I let t equal 1 over n. That will be limit t goes to 0. 1 over t sine t, which I know it's 1. So that will be 1 plus 1, which is 2. Understood. N sine pi over 3 over n. Okay. Yeah, I need to find this limit. N goes to infinity. N sine pi plus 3 over n. Okay. You know that. Yeah, let me check the sine pi plus 3 over n. If you open it, that will be sine pi cosine 3 over n plus sine plus cosine pi sine 3 over n, using the sum of the angles for sine. That is 0. This is 0. This is minus 1. So it will be minus sine 3 over n. So this is limit n goes to infinity of minus n sine 3 over n. Now I'll use the let things. Let t equal 3 over n. So that means n equals 3 over t. So this limit will be limit t goes to 0 minus 3 over t sine t. Well, this is 1. So I have minus 3 times 1, which is minus 3. Since I'm now making it that t equals to 0. N sine pi plus 2 over, I think the same idea, and it will go to minus 2. Since this, yeah, n sine pi plus 2 over n. Yeah, this is sine pi plus 2 over n. If we do the calculation, like what we did here, it will be minus sine 2 over n. Then you can do the calculation. I will leave it for you. And I think we did something similar, but now it's a negative. So this is limit as n goes to infinity, tan 2n pi over 2 minus 8n. You can take the limit inside. That will be tan limit n goes to infinity, 2n pi over 2 minus 8n. That will be tan 2 pi over minus 8, which is like what we did here. No need for n. In gun. So it's pi over 2. Yeah. No need for n because it's the same degree. Huh? No need for n. It will be 2 pi over 8. Just to be sure about the way we wrote it. Same degree, so just right away we take the coefficients. No need for it. Okay. That will be what? Tan minus pi over 4, which is minus 1. So let's compare this to minus 1. Yeah, let me do this one, then I will stop because I don't want to have long videos. Okay, so I have limit n goes to infinity, n cubed is minus 2n. So I think it will be infinity times 0. So let me do it by L'Hopital's rule. So I have x cubed e minus 2x. I need to find this. X cubed e minus 2x. If you notice, I can rewrite this, since it's infinity times 0, I can rewrite it x cubed over e to the power 2x. Now it's what? Infinity over infinity. So do L'Hopital's rule. You have what? 3x squared over 2e to x. Still, it's infinity over infinity. Still, it's infinity over infinity. Do the L'Hopital's rule again. You have 6x over 4e to x. Still, it's infinity over infinity. Do L'Hopital's rule again. You have what? 6 over 8e to x. Now it will be a number over infinity, which is 0. So let's compare this to 0. Yeah, let me stop the recording because you don't like to have long videos. Thank you.